every challenge question, chapter 7 from book 2. It's the last of the trig chapters. I thought this question was pretty cool, to be honest. We're just going to do a bit of SOHCAHTOA to find out this length, this length, this length, and this length. So, okay, well, this is just y cos b. It's just the unit triangle scaled up by factor y. So if this was length 1, this would be cos b, and this would be sine b. So it's just y cos b and y sine b. SOHCAHTOA also gives you that. And likewise down here, this is x sine a and x cos a. Now, this is the cool bit. The area of the three triangles. The obvious thing to do is say that the area of T2 is a half times y cos b times y sine b, because that's just a half times base times height. But don't do that. Notice how these two lengths are equal, right? Because they're representing the same length. So the area of T2, call it half times x cos a times y sine b. And for T1, call that a half times y cos b times x sine a. Just flip them over. And the reason you want to do that is because, of course, the combined area is just going to be a half times x times y times sine of a plus b, just this whole angle here, a plus b. And that's great, because now we can just say, well, that therefore this plus this equals that. Cancel the half xy's, and you end up with that formula that we know about, which is pretty cool. I quite enjoyed that one. Show this and this. Okay, we'll just expand out cos. I guess left-hand side, right-hand side stuff cancels. You end up with it very quickly. Hence show this thing here. So just replace a plus b with p and a minus b with q. This, of course, means that a, if I add these two things together and then divide by 2, is this, and b, if I do this, take away this, and then divide by 2, is that. So I think I can just replace all of that wholesale into here. A plus b becomes p, a minus b becomes q, a becomes p plus q over 2, and b becomes p minus q over 2, and we end up with part b. Hence express this as the difference of cosines. So, okay, well, it looks like here, let's compare this job with this job here. There's a minus 2 in front, so I think I just have to times everything by minus 3 in this line here. That gives me a 3 in front there. Sorry, minus 3 over 2, of course. And now this thing is starting to look more like this. I just need to set p plus q over 2 equal to 1x, I guess, and p minus q over 2 equal to 7x. Now, this is awkward because this should really be the bigger one, so I'm just going to swap these over. Of course, it doesn't matter swapping these over with multiplying. Multiplying is commutative, so I'm just going to swap them over. Makes the maths a little bit easier on my head. I'm looking for two numbers that add essentially to make 14 and take away to make 2. That would be 8 and 6, so that's my answers, I think. I think I could just shove those in there, and I think that's the difference of two cosines that they're looking for. The reason, of course, that you'd want to do this is because let's pretend you were integrating this function here. That's much easier to integrate if you change it to be like this, because integrals of things that are adding and subtracting is super easy. You just integrate the things separately. Whereas this, not so easy to integrate. So yeah, that would be the reason that's helpful. 2 is the same question, basically, as 1 was. First, we need to start, like, notice how part A, they've taken us straight to this line, which was part B of the previous question. So let's start by setting up part A ourselves. And we're looking for sine and cos here, rather than sine and sine. So it feels to me like we should probably just use sine and sine here to get the non-cross term there. Or sorry, to get the cross term that we actually want here. So yeah, let's set up sine and sine and add them together. This obviously equals this. So I've just written part A for myself. And of course, I'm going to end up with sine A plus B plus sine A minus B is 2 sine A cos B, which is useful because that gives me sine plus sine here and the cross terms here, which is what I wanted. So now I can set P equal to A plus B. This is the same thing as we did last time. You get the same results. And you shove them in and you get the result they were looking for. Hence, or otherwise show this thing here. Well, okay, this is very straightforward now. The 2's match. So I just need p plus q over 2 to be this and p minus q over 2 to be that. And solve these. Of course, all I really need, if you just imagine timesing both of these sides by 12, I guess, would be one way of thinking about it. I think I just said essentially that p plus q needs to make 11 and p minus q needs to make 5, which is obviously going to need to use 8 and 3. And then I just need the spare leftover over 12s to make that actually work. Because if you make them over 12 and then over another 2, you get over 24. And then obviously throw the pi's in. You can simplify those down to get this. And therefore, 2 sine this cos that, going back a step, is sine of p plus sine of q. So sine of this plus sine of that. You should be able to work out these in your heads. That's going to be root 3 over 2 because this is the same as a third pi. And this one is just root 2 over 2. Add them together and you get what they wanted you to get, which is good. This question is absolute BS. I don't understand why modeling in maths exists. I'm just gonna say it out loud. You know when people who like English like reading books and poems and plays that are fictional, no one forces them. No one says to them, "Oh, Why don't you do something useful with your English skills, like reading journalistic articles? No, that person just enjoys reading poetry. That's fine. Let's just leave each other alone. Why are you forcing me to answer a question about microwaves? Why do I have to use my maths to do this? What's the point? I don't care. Okay, rant over. That's just I've said that I would do every challenge question in the book, so I'm going to. Unfortunately, this challenge question refers to a different question that's not a challenge question, so I'm under no obligation to actually complete this question. So I'm just going to write down all the answers that came from the from Solution Bank. So okay, not going to bother with that. I do have to do this, however, and I think I've already made it clear that I do not want to do this in any way. So I've made that clear. Part A. Estimate the range of the locations in the oven. Is it an oven? It's not. It's not a microwave. Oh, oh dear. Microwave. Who? Who? uh, Okay. So the energy is proportional to 1 over the electric field strength squared, apparently. So I can set the, sorry, not 1 over, directly proportional to E. Yeah, cool. The energy required is also going to be inversely proportional to the time taken. Like if it takes more time, that means you required less energy to put into it. You could, I think that's essentially modeling the fact that you could turn the microwave. Don't they have that little setting where you can turn the hertz or watts down or whatever? I don't care. Energy is proportional to 1 over the time taken, I think is what we can write. And then we can combine the electric field strength with the T to make this proportional to that. And then just say equals K over T like you did at GCSE. And now they've given us the information that it takes 20 seconds, so T is 20 um, at maximum strength. Now down here, maximum strength was 1950, so you can put that information in here and solve for K, and then you get this equation here. And now that's essentially, we're looking for the times it takes longer than 30 seconds. Let's just find, sorry, not the times, the positions in the oven, it takes longer than 30 seconds. Let's just find when T is 30. Let's just find the critical points. So T is 30, puts in here, we get an E value of this, and then we can put that E value into this to find X, which is the position in the oven. So let's do that. We're going to take away this, we're going to divide by 250, we're going to do sine inverse, and eventually you'll end up with our principal solution of this here, I think. So I did sine inverse of this thing, and then that's equal to obviously the thing inside the bracket. Before you start solving, you need to find all the other solutions. So if we get out the sine graph, we've got one solution back here, which means if we're looking for this whole thing to be a negative. So if we add, if we do pi plus the modulus of the thing that we just found, we'll find the next solution. So that's what I did. I did pi plus 0.445. And then if you just do minus 0.445 plus 2 pi, you'll get to this solution over here. And then if you just add another 2 pi to that, you'll get another one, and another 2 pi to that, you get another one, and so on. I'm going to stop there because when you then calculate the actual x values by adding this times by 25 divided by 4 pi to all of them, you get this. And this last one is bigger than 25, which is relevant because the question says that the oven is only 25 centimeters large. So any bigger values get you numbers that are now completely irrelevant. So, okay, these are all the answers that are relevant to me. You can either go back a step, because these are the critical values, right? This is the positions where it will take exactly 30 seconds. So to do more than 30 seconds, are we in between these two and in between these two and so on? Or are we between here and 0, in between those two, and from here to 25? Remember, 25 is the max, so this is kind of irrelevant. Well, it's actually the latter case. It's between 0 and here, and that's kind of logical. If you put it right at the edge of the oven, it's going to take longer. You can also work your way back and actually decide what you need to do with the signs back here when you say that E needs to be less than this. Sorry, hang on. If you want to put, yeah, E should actually be less than that. So you can do that way. Or you can just be logical and say if you're at the edges, like between here and 25 or between here and 0, that's clearly longer than 30 seconds, and that leaves you in between those two in the middle there. State 2 limitations of the model. I don't own a microwave. That's one limitation, so it's pointless to me. And limitation number 2, who melts chocolate in a microwave? I used to be a professional baker. Let me tell you something. Set up a bain-marie. You get a pan, you put some water in, you put a glass bowl on top, not plastic, obviously, you'll melt it. Put a glass bowl on top, melt the chocolate down gradually. A microwave's never going to melt the whole thing at once. You're going to burn the middle of it while barely melting the outsides, unless you use very small blocks at a time, which is a waste of time. Bain-marie, melt it nicely, get a little wooden spoon, stir it up a little bit. By far the better way to do that. Number 1 challenge here then. So okay, we'll start left-hand side or right-hand side. Left-hand side looks easier. We proved, I think, earlier, maybe at some point, that cos 4 theta, did we? Well, okay, I don't think we did actually, but cos 4 theta, we can use a little rule for this. Did we do it in the previous chapter actually, maybe? I'm not sure. This is the rule for cos 2 theta. Just double the thetas to get cos 4 theta and 2 theta here, and replace that in there. And likewise for sine 2 theta, double all three of these thetas to get this, and replace that in there. And something nice happens here, which is the top actually factorizes, because you can imagine it as 2x squared plus x minus 1, which factorizes to this. And the bottom also factorizes because it's got a shared sine 2 theta in it. And then this and this cancel, almost. They don't quite, but they do if you just put a minus in front. And then this just sorts out quite nicely, I think, if you just replace this using this formula up here. Is it this formula up here, or is it not? Yeah, it is, because you just add 1 to both sides, and you get the 2 cos squared. And then cancel these with this, and the 2's obviously, and you just end up with minus cot, which is what they wanted you to get. Part B is cool, because that does directly use the kind of idea we were doing earlier. In the formula book, you get this, which we sort of proved earlier, just a slightly different form of it. But anyway, that's cool. Swap these two results over to get this. I actually put this one right at the front. Okay, but now look at these two things here. I think I can kind of use these two. I'm going to ignore this for a bit, but use these two here to say this is 2 cos of 5x plus x over 2, which is 3x, into 5x minus x over 2, which is 2x. And you get this result here, which is quite cool, because now I can factorize out cos 3x. Cos 2x plus 1, is that what we saw again 2 seconds ago with this identity here? You get this, and that's what they wanted you to get, which is good. So we're done. Question 2, I made a super old video on the original channel about this, so you'll forgive me for ignoring this question and just going straight into the slides that I made for that. So I am going to do this. It's just going to look how the way that I did it originally. This is the unit triangle, 1 sine theta cos theta, put a big circle around it. And then what we can do is if we draw a line, this is the diameter of the circle, of course, because this is a right angle. Circle theorems work both ways around. If this is a right angle, then this is the diameter, which means halfway along you have the center with a half here and a half there. That's cool. That's our setup then. We're going to first draw the altitude of the triangle up to make a right angle here, which is cool because that means I can think of my regular unit triangle, 1 cos theta sine theta, and I've got more right angle triangles in here that I can find some scale factors for. So for example, this triangle here with angle down here of theta, right angle here, of course, hypotenuse cos theta, clearly has a scale factor of cos theta. So therefore this length here, which is equivalent to this length here, is just cos squared theta. And this length here is sine theta cos theta, which is this length here. So let's add those to the pictures. And that's great, because I think what I can say directly from this is that, what can I say here? Is it that, first I need to do a tiny bit more work, don't I? Yeah, cool. If you draw a line going to the center here, this angle here is 2 theta, and it's 2 theta because of the circle theorem that says angle at the center drawn from one arc is double the angle at the circumference drawn from that same arc. So this angle here is double this angle down here. A lot of people think of it as the Starfleet circle theorem if you haven't been taught it properly. But anyway, this is 2 theta. We can now do some stuff here, which is saying this is a half because it's the radius, of course. And therefore, this length across here, if you've got a unit triangle with 2 theta as the angle, that just makes this length cos 2 theta and this length sine 2 theta. But of course, we've got that, but with the hypotenuse being a half. So we just need to halve all of this, and we end up with this length here being a half cos 2 theta. You could also do SOHCAHTOA to find that out. But anyway, I think now we are at a circle theorem, and that circle theorem says that cos squared of theta, at an identity, cos squared of theta is equal to a half, which is this length here, plus a half cos 2 theta. Which we can just double everything for and take away 1 and whatever. And we end up with this one, which is the first thing they asked us to prove. And the other one they asked us to prove was this sine 2 theta thing here. Well, like I said here, over here, this is just a half sine 2 theta, which we already know is equal to cos theta sine theta. And so we just double everything and we end up with that identity as well. Thank you for watching. I'll see you next time.